Welcome to our tutorial for question 11 of our weekly review. Question 11 is asking us to find the unit rate or the rate of change or slope of both of the functions that are given to you, and then compare the functions with each other. In this particular case, we want to make sure that we're defining a few terms, and then we'll take a look at what this is going to look like for us. So first, when we talk about rate is another way to describe rate of change or slope, and we've talked about this lots before in lots of our other equations. Question 8, 9, 10, 11, 12 all deal with these linear equations. A reminder that our rate of change or our slope in an equation or a function is always going to be the m part of our function. That is our slope. And remember that m always is what goes with the x or is being multiplied with the x that's there. When we talk about unit rate, we're talking about a special kind of rate, and that's simply a rate that shows the change per one of something else. That's what unit means. We're talking about one of something. So when we describe a unit rate, we're going to describe per one of something. Now the nice thing is when we work with linear equations, tables, and graphs, in general, we are already working with a unit rate. But I do want to make a quick note here as we look at these for some things to be aware of. If we're looking for a unit rate in tables, and we ended up with a table that looked something like this, and we have talked about this before, I think back in question number 8 or 9 of our weekly review. The first thing that I would notice is that my x value is not moving or changing by 1. I kind of have a random change that's happening over here. I grow by 4, then I grow by 3, then I grow by 2, then I grow by 3 again. It's not a constant change, and it certainly is not a constant change per one of something. So looking at a table like this, I could not find the unit rate just based on the table that was given. So make sure that if you ever see something like this, you translate that table into a table that will show you the rate per one. In this case, I've simply extended that table out. So now I've included those values 1, 2, 3, 4 to make sure that I'm actually counting by 1. I can fill in the values that I was given. Here I had 16 and 28, and I could start to guess and see if maybe counting by ones worked. In this case, 0, 1, 2, 3, 16. That doesn't seem to match a pattern. I could try again, and I could do like 0, 2, 4, 6, and then 16. That also doesn't match a pattern, and we could do that until we found the pattern. However, if you haven't noticed this yet, you can also find that rate or the unit rate by dividing our y value by the x value. In this case, I could pick 16 and divide it by 4, or 28 and divide it by 7. Both of those are going to give us the same value of 4, which when I start to plug into my table, I'm going to notice that that works. So 4, 8, 12, 16, 20, 24, and my pattern works in this example that I have. So you can find the unit rate anytime by dividing the y value by the x value that you are given. Okay? And another quick note, because we have talked about this before, the unit rate then is actually showing up on the outside of our table. That is our slope. We've already described that as being the rate of change or the slope. So you can find that unit rate by dividing the y values by the x values. And once you have a rate per one in a table, you're welcome to simply look at the slope, which we know is how much each y value is changing by per one change of x. Let's go ahead and look at a unit rate in an equation. This is really simple. In fact, we've already described that our unit rate in an equation is simply our m value or our slope And remember that our m value is always what goes with the x, or what is being multiplied by the x. In this case, it's y equals 3x plus 12, so 3 would be my unit rate. If I wasn't sure of that, I could certainly create a table, and here I've simply made a very quick table. And I know that my equation would start at 12, and I'm increasing by 3 each time. Remember, we've described that you can find the unit rate on the outside of our table, where it's showing the change per one value of y there. If we look at a couple other equations that we have, here I have y equals 2/3 x plus 4. I also have y equals 9 minus 6x. Well, in the first example, I'm going to notice that I have 2/3 is with the x. That's being multiplied with the x, which means that my unit rate is simply 2/3. In my second equation, it looks a little bit different, but in this case, the rules stay the same. I know that my unit rate is always what goes with the x, or what is being multiplied by the x. In this case, my unit rate is -6. If I'm looking for a unit rate in a graph, if I was given a graph and I'm looking for a unit rate in a graph, I'm going to do some work that we've done before, and that is create a growth triangle that's showing the rate of change, or the slope of the graph. If I do that, and I were to show that something, in this case, grows by 8 and changes by 2, well, we can simply create a fraction that shows us our rise over our run, which would give us 8/2 equals 4. And again, you can do this on any point that is in your graph, or any 2 points that are in your graph. So I could do that with another growth triangle of 16/4 equals 4, and that would also show you your same rate of change of 4. Now, one of the things that's interesting here, if you go back to what we talked about in our tables, in the original tables, when we said you could pick any y value and divide it by its corresponding x value, that is exactly what a growth triangle showing rise over run is. Remember that rise is our vertical line, or our y value, and run is our horizontal line, or our x value. So all we've done here is the exact same thing that we've seen in our table, but we've done this with a growth triangle instead. That should give you a sense of how to work with our unit rates in linear functions. Make sure that you are going back and reviewing any of your weak points on questions 8, 9, 10, 11, 12 that all deal with linear equations.